Okay, good afternoon, everyone, and welcome to this Oxford Martin School lecture. It's a great pleasure to welcome Martyn Unsworth from the University of Alberta in Edmonton, in Canada. Martyn is an Oxford Martin School Fellow, and he's here because he's aligned with research that we're doing as part of one of the Oxford Martin School programs, which is called RESET, or Rethinking Natural Resources. And that program is about looking at ways of valorizing the entire geothermal system, if you like, from energy generation to metals and all sorts of other direct use activities. And our target research area is the Caribbean island of Montserrat. Someone has to work there. And Martyn is actually undertaking one of the geophysical parts of the program. He'll be imaging the subsurface with the techniques he's going to describe today. By way of a brief biography, Martyn is graduated in physics, natural sciences, from the University of Cambridge, and did his PhD there in geophysics. After postdoctoral positions in British Columbia and Washington State, he then moved to the University of Alberta, where he's been for about 25 years or so. Martyn will show you some of the work he's done, which is astonishing in its own right. But if he doesn't share with you one important detail, I thought I would, that this is field geophysics, and this is quite extreme field work. So us geologists, we pootle about with our hammers and our hand lenses. This is a different order of activity. He's worked in some extremely remote and challenging places. Off the top of my head, Antarctica, Peru, Bolivia, Chile, Iran, Taiwan, China, Canadian Arctic, Alaska. That's quite a lot of exciting places. And in each case, the challenge is to get all the kit there, to make sure the helicopter is getting you to the right place, to get all the kit back, and to make sure you don't get attacked by a grizzly along the way, or a polar bear, or whatever it might be. Okay, so without further ado, Martyn will talk to us on that topic, using geophysics to understand volcanic eruptions and search for geothermal energy resources. And I'd like you just to join me in welcoming him to the Martyn School. Thank you.
Great, thank you, John, and for the welcome, and for the Oxford Martin School for making this visit possible. So I'm going to give a very general talk about geophysics and about some of the applications. And also, as John mentioned, I do go to some interesting places, some people tell me. So I'll kind of give you an idea sometimes of what's actually involved in collecting the data. So just to kind of start, I'm going to focus on two areas where information about what is underground is useful. And the first is in volcanic eruptions. So volcanoes, as we can see here, spend most of their time not actually doing anything so exciting as this. But when a volcanic eruption occurs, it can have huge impact on the people living nearby. And one of the big challenges in volcanology is trying to give accurate information during a period of time when nothing is happening. Perhaps a volcano then becomes restless, and then the media start becoming very excited. And then trying to be objective about what might happen, what the consequences might be. So obviously, once a volcano is erupting, this is Volcan Calbuco in southern central Chile about 10 years ago now. So this eruption had a big impact. It didn't actually hurt anyone, fortunately, but that's not always the case. So kind of looking below the surface is what we need to do to really have better information about what might happen. And we know that volcanoes, when they erupt, they're tapping into magma that is coming from a magma body, a region of partly molten rock below the surface. So geophysics is a way of looking down there and seeing what's there, how much rock is molten, where is it, and then trying to make some educated guesses about what might happen next. So that's where I'm going to be talking about geophysical exploration. So this just kind of shows a little bit about some of the ideas about molten rock under the surface of the Earth. So I guess in the old days, you know, the geology textbook shown here top left, you know, there was the idea that magma bodies were 100% molten rock, and they sat there until they erupted. I think it's fair to say that a combination of geophysics, petrology, such as John's work and others, has really shown us in the last 10 years that things are more complicated than this. Quite often, we're not dealing with molten rock. Often we have a mixture of crystals, and in between those crystals is a liquid, molten rock. And these things can sit there for a very long time. People always laugh about geology, you know, a million years is a short time. Well, people talk about cold storage in these magma bodies, and cold storage is usually at 600-700 centigrade, not cool for most of us. But the idea is the magma can sit there, kind of not doing anything, for maybe a million years, and then suddenly something triggers it, and you get a big eruption. So we're getting this view of volcanic systems that is becoming ever more complicated, perhaps more realistic as well. Shown on the right is another sort of recent synthesis and result that we see the volcano erupting at the surface, and we know where the magma has come in at depth in the earth. But in between, it's not just a straight journey up to the surface. What seems to happen quite routinely is that the molten rock, the magma, is rising upwards and is spending time sitting, maybe undergoing some chemical reactions, and then moving up step by step to the surface. So we've gone from this very simplistic view, if you like, of large regions of completely molten rock to systems of mixtures of rocks and grains to these multi-level systems. And geophysics is a very powerful way of looking into the subsurface and seeing what is there now. And then from that, we try and make predictions about what might happen next. Well, another reason for looking under the ground in volcanic areas is to understand the potential for geothermal energy. So as most people are aware, we're really at a time where we're looking with a certain urgency to find ways of producing electricity and power that does not involve large amounts of carbon dioxide being put in the atmosphere. And I work in a lot of research in Canada in geothermal energy, trying to develop methods where we can extract heat from the ground and put that either into a power plant to make electricity or just use the heat directly. So in a typical geothermal system, as shown here, we're often trying to find some source of heat. So for a geothermal power plant or heat system to work, we need three things. We need something hot. We also need water or some other fluid to bring that heat to the surface. And the third is we need rocks which are sufficiently permeable, they're fractured, they're broken, to let the water or whatever fluid we're using move through. So in the conventional form of geothermal energy, which has been around now more than 100 years, this kind of works fairly well. It's economic compared to other methods of generation. But what is required is knowledge about what's under the ground. And this is perhaps one of the biggest challenges in developing geothermal energy. Solar and wind power are great renewables, and the great advantage they have is you know what you're going to get. You know how many hours of sunlight per day you're going to get, you know what the wind's going to be like. The problem with geothermal is we have uncertainties in our knowledge of what's below our feet in the ground. And that's where a combination of different geoscience methods can come together and give us information about that to reduce the risk. So we'll talk in a minute about the different phases that go in. So typically at the surface, we might actually see geysers, we might see hydrothermal alteration. Don't always see those, but what we're searching for is a layer where we have some heated water. And the idea is we're going to drill into that. 1 to 2 kilometers is often a good depth. It gets hotter as you go down, but deeper drilling is also expensive. So a lot of compromises, and more information generally is helpful to inform those types of decisions. So you don't have to make electricity for geothermal to be effective. And there's countries around the world that make extensive use of geothermal power. If you're getting water up to the surface at 10 or 50 or 100 centigrade, current technology is not really favorable for making electricity efficiently. So in those cases, you can use that heat directly. Maybe heat pumps, I know, have been developed quite a bit. Well, this is one application. I think this is not in business anymore. A place in Idaho, they were rearing alligators in this geothermally heated pool. Maybe not the most usual type of application, but it certainly was going on. This is a picture in the Netherlands where they're heating a greenhouse with geothermal heat. And every joule of heat that you put into a plant like this is heat that is not generated by burning hydrocarbons. So direct use has a huge, huge potential. If you're getting water coming up under pressure at more than 150 centigrade, then it becomes possible to make electricity. And at 150, it's kind of challenging to do it efficiently. But once you get to 200 or 250 or 300, then you start to be able to run a power station very similar to what you would by burning coal or oil or gas, but obviously with 100 times lower carbon emissions. So Iceland's been a country that's made great use of this. Most people think of Iceland when we talk about geothermal electricity. But actually, I'll show in a minute, the United States is actually still the largest producer of geothermal power in terms of actual megawatts. So the idea of a geothermal power plant is as follows. We've identified some region underground that's being heated by some magma, perhaps, and it's got enough fractures and enough water down there to be efficient to bring that up. So if everything goes right, you can just bring that hot water up, put it through a power plant, and the cooled water is typically very saline, so you just put that back where it came from. And if you manage the input and the output of the reservoir correctly, you can run this for decades, if not longer. So countries that do this produce electricity which is similar in price to what you would get from conventional non-renewable types of electricity. You know, typically 2 to 10 megawatts of electric power is quite reasonable per borehole. And we'll talk at the end about ideas to try and increase that, you know, significantly in some parts of the world. So geothermal is what we call baseload. It works 24 hours a day. And it can be combined very well with other renewables such as wind and solar, which are not always available. So in the Canadian Arctic, one of our big challenges with renewable energy is it's dark half the year. There's no lack of wind, but there's 6 months when the sun is barely above the horizon. So geothermal can often fit into a mix of renewable energies. So most of the geothermal development to date, such as the work being considered on Montserrat, is on volcanoes or in regions where plate tectonics is creating fractures to bring that heat up to the surface. So there's a lot of technical challenges, but a lot of experience has been gained with oil and gas industry drilling holes in the ground. So we're seeing in Canada a lot of the people who no longer work in oil and gas have actually transitioned into geothermal energy. They're drilling holes and they're bringing liquids up. It's really very similar to what they were doing before. So here's just kind of a list. It's a couple of years out of date, but I did check the sequence yesterday. It hasn't really changed. This is the countries that produce geothermal electric power. And number one is always a surprise to people. It's the US, megawatts. In fact, if Nevada was an independent country, Nevada would be the number one producer still. Indonesia sits there number two and recently kind of got ahead of the Philippines. So these are all volcano-based systems. Turkey has a lot of places where the Earth's crust is being stretched in the west. New Zealand, Mexico have volcanic systems, so does Italy. Well, I put Canada on this list because we currently do not generate electric power from geothermal, and we do have significant potential. But note the percentage. Obviously, it's a lot in megawatts, but it's 0.3 of the American electricity power production is coming from geothermal. So the fact that these numbers are quite small is encouraging that there are huge openings here to actually develop these systems. So let's kind of talk a little bit now about exploration. So this is the part of geothermal energy development that I work in. Someone's wanting to develop some power production. We need to know what is under the ground. And the more we know about the subsurface, the lower the economic risks that will be there. So I should have maybe put pound signs rather than dollars up there, but you know, we tend to go through different price regimes. And often things start out, people look on the surface and say, okay, is there any evidence for hot water under the ground here? So maybe you see some geysers, or maybe you see some warm springs, or maybe you see some alterations, some strange chemical processes have gone on. Clues that there is something down there. I'm not saying that geology is a cheap exercise, but you know, a person goes around on the surface and is just simply looking. We usually then proceed, if things look good, to actually using geophysics to look under the ground. And I'll be the first to admit this is where the price starts to go up, because we're typically having to move equipment around that's capable of sensing 1-2 kilometers below the surface. And finally, we get to a point where sometimes the companies say, well, let's just keep doing geophysics just to be really sure. And I usually say, well, you can, but there comes a point at which someone's got to pony up the money and actually start drilling wells. And this is the point at which you move from, you know, hundreds of thousands of dollars to millions to tens of millions of dollars to drill. And I mentioned before, typically we're drilling down 1 or 2 kilometers. That gives us a compromise between getting to a high temperature, but not spending so much on drilling that it kind of makes things uneconomic. So most of my talk now is going to be about some methodologies that we use for doing this. And if you're familiar with oil and gas exploration, that uses a method called seismics. You send sound waves. If you're looking for hot water and related materials, then what we do is we measure a rock property which is called resistivity. So this is telling us how well does the rock conduct electricity. And on this color scale, I'm going to use this color scale throughout the talk. What we see is igneous rocks, cold, dry rocks tend to have a high value, so I'm going to color them blue. Sedimentary rocks tend to be containing some water, they're in the middle. But down at the bottom, we have these materials which are interesting for geothermal, maybe salt water, brine, maybe partial melt, maybe the effects of that water reacting with rocks. So we want to measure this rock property, but we do it from the surface using a technique of sending radio waves into the ground. So just to look a little bit more into detail what a rock might look like, a lot of rocks that we see in the earth are a mixture of grains. So the rock grains are shown in white. They generally don't conduct electricity. But in between them, there's often a liquid. And that liquid, in many cases, conducts electricity. And in this case over here, it could be salt water, or it could be molten rock. Regardless of which it is, the liquid has a really big effect on this thing called resistivity. So if we measure the resistivity, we can then work out what type of liquid is down there, how much of that liquid is present, and start to get a better idea of what is the potential costs-benefit analysis for developing geothermal energy. So to measure that resistivity under the ground, there's various ways of doing it, but the way we adopt is we measure natural radio waves. So these waves are coming from space. They hit the Earth's surface, as you can see here, the blue wave, and most of the energy is reflected back where it came from. Some of that energy, that radio wave, makes it into the ground, and we sit at the surface and measure it with basically what is a large radio receiver. So these things work out with batteries and things at about 70 to 80 kilograms each. So you can carry them. If you've got a helicopter, it's a lot more convenient. And we've done field work in different places with everything from helicopters to boats to horses, which I'm never doing again, or graduate students in Canada. That's kind of often the most economic method of doing this. So this is our method. It's a radio receiver, basically. So I'm going to go through now a series of examples of how and where we've used this and just try and give you an idea of the different types of results that we've been able to get from these studies. So the first case is in the Andes. So South American continent is shown here. And what we see is plate tectonics is active here. So the plate which sits under the Pacific Ocean, the Nazca plate, is subducting. That's the geological word for one tectonic plate moving below another. And that process has had a very profound impact on this part of South America and indeed many parts of the world. So the subduction zones generate big earthquakes. They also provide a source of water which causes melting of the rocks down here at 100-kilometer depth, which gives us a nice line of volcanoes. So most volcanoes in the world are of this type. They're in lines along subduction zones. And in South America, if we kind of look in a bit more detail, we actually see that the volcanoes are not everywhere. There's one line of volcanoes up here in the north in Colombia and Ecuador, another one from Peru to northern Chile, and then another one in northern central Chile. And these gaps are places with no volcanoes. And that's actually been discovered to be due to the fact that sometimes the plate that's going down doesn't actually go down for various reasons. It actually flattens out. So it's kind of again, obviously there are some places here which are going to be better for geothermal power. If you're using volcanoes for your heat source, then these regions where the plate is going down at a steep angle are the places to start looking. So I've been working in a number of parts of the Andes, partly in the south at some volcanoes here, but mostly in this region here we call the Central Volcanic Zone. So this is a region, southern Peru, Bolivia, northern Chile, parts of Argentina, where the Earth's crust is very thick and flat and high, and there are quite an active set of volcanoes. Each of these countries has been looking at, first of all, understanding volcano hazards, and also looking at the potential for geothermal energy. But one of the challenges we often come up again with geothermal energy is it's not just the science and the technical aspects. A lot of places in Latin America, they have an election every 4 years. And when elections happen, there's a complete change of government. So trying to get people to think about economic development and energy projects with a more than 4-year time span kind of can be a problem. So each of these countries, however, recognizes that they sit on some valuable resources. And most of the Andean countries are very actively developing this form of electricity. So one area we've worked in Bolivia, I'm going to talk more about a volcano aspect than a geothermal aspect, is kind of down here. If we look in the central volcanic zone, right towards the south, there's kind of our line of volcanoes, but off to the east, there's a set of isolated volcanoes. And we became interested in this area because several of these volcanoes are showing signs of uplift. The surface of the Earth is moving up at about 1 or 2 centimeters per year. All volcanoes do this, but these volcanoes have been doing this for 50 to 60 years and don't seem to show any sign of going down. So the idea is maybe we're getting a large input of molten rock there, or maybe something unusual is happening. Obviously, it's a pretty remote part of the Andes. You know, the local llamas here don't kind of ever seem to me to be too worried about an eruption. But if this volcano, Urubuncu, was to erupt, as it has done in the past, it would be a pretty catastrophic eruption. So Urubuncu is slightly over 6 kilometers high, and it hasn't erupted for 270,000 years. But it's got all these signs that it may still be active in some way. There's steam vents, there's small earthquakes, and there's this upward movement. So we applied, this was the first South American project I did, geophysics to try and understand what was going on. So I went back to Bolivia last year and was reminded by all of the great things I like about Bolivia, but equally about the many complications of working in lots of Latin American countries. So this is actually showing the driving conditions, which are always interesting. Most of the time, there's not really a road, or if there is, it's a dirt road. This is actually the best highway in Bolivia. It's the Solaribu Uni. It's the only place I know there you can drive at more than about 100 kilometers per hour. So just getting the equipment to the field was about a month's work, dealing with customs agents, rental vehicles, strikes, all sorts of different things that are just part of daily life in Latin America. When we get to the field, and our equipment, these big radio receivers, we put them out on the ground, and we typically leave them overnight. So that was a bit of, got to make sure they're in a place where no one's going to steal them, and they'll be there in the morning. But typically we spend about an hour or two. We have some Bolivians who come and dig holes for us, and we put the equipment in the ground, we check it's working, and then we come back the next day, take the data off. So the great thing is we're not generating any signals. It's all natural radio waves that we're measuring. So sometimes the driving conditions are a little bit kind of unpredictable, but there's a road up this volcano because it was a sulfur mine until quite recently. So most sulfur is now extracted from natural gas as an impurity, but until that was easy to do, Bolivian miners lived at 6,000 meters and dug sulfur out of these volcanoes. So a lot of things kind of go into these projects to kind of make them work, and sometimes I come back saying I'm never going again, and I usually forget after a few weeks and go back again. So here's our results from Urubuncu. So this is the inflating volcano. So to go from the data we collected to these colored images is a lot of work. We're typically processing data in various aspects on computer clusters. But at the end of the day, we get a resistivity model. And remember, red is going to be low resistivity. That's stuff that conducts electricity. So right below Urubuncu, we see a really big red zone down here at about 15, 20 kilometer depth. Well, before we went there, we knew that the seismologists had measured anomalous properties of the rocks, and they'd said this is the biggest magma body on Earth. It's about 100 kilometers across, it's about 15 kilometers below the surface, and there's good geological evidence it's caused really catastrophic eruptions in the not so distant past. So we measured a property down here, and the rock properties here can be interpreted by lab experiments. So it used to be we had no information about exactly how the rock properties depended on the chemistry. And that made things quite difficult to interpret the data. But thanks to a lot of people who are working in this area recently, we can actually now be a lot more quantitative. So I'm not going to go through the analysis, but just to kind of explain that this layer down here is probably 20–30% molten rock. So there's a thing called eruptibility in geophysics with volcanoes. You have to have probably 50% molten rock to actually get an eruption triggered. So this rock layer sitting down there 15–20 kilometers is significant, but we don't see any signs at the moment that this is going to come to the surface and cause another large, very catastrophic volcano. But what had caught our eye was these other red bodies up here nearer the surface. And what we had done is we actually went through an analysis. So just to backtrack slightly, sorry, that deeper body, working with John Blundy, we found that the magma actually had a lot of water mixed in with it, an unusual amount, about 7%. So, you know, I guess geophysicists, we just calculate numbers, but John worked out that the volume of water was about the same as Lake Michigan. So I guess this is a graphic way of telling you there's a lot of water down there in the Earth's crust. And then, of course, if you have articles like this, there's all sorts of online science sites that come up with interesting ideas. And people were writing, well, why don't they drill down and get the water out? Well, it's 15 kilometers. That's obviously not practical. So this was kind of a surprise. You know, these very wet magmas are down there. And it's only really possible to say that with this combination of geology and geophysics together. So looking nearer the surface, we'd seen that there was this shallow conductive body here, low resistivity, about sea level. Remember, sea level is 5 kilometers down in this part of the world. And it's quite common to see something below volcanoes at that depth. But this was quite an unusual one. And the long and the short is, we no longer think this is molten rock. It's just not consistent with the experiments. It's probably a region of salt water, of brines. So this is kind of an interesting result. We're starting to become able to say, not just that it's a liquid, but which liquid is it? Because that has a huge impact on whether the volcano is going to erupt. If you're nearer the surface, it tells you about the geothermal energy potential. So this kind of avenue of working with geology and geophysics together, I think, has been quite productive. So kind of to summarize, I was very impressed after a couple of years of this project that John and one of his students in Bristol had kind of worked at looking at all of these different volcano studies to try and see the bigger picture. And we often see that there are magma bodies or zones of molten rock at several depths. There's often a shallow one, which is often, we think, due to brine. Further down, we get into regions of molten rock. And we start to see this pattern, not just one volcano in Bolivia, but also in many volcanoes along the length of the Andes. So this starts to give us a predictive tool for understanding the behavior of many other systems, not just our study location. Well, changing topics slightly now to a different type of volcano. This is Mount Erebus in Antarctica. And I worked there about 10 years ago on a couple of projects. And a lot of people think, well, they don't realize there's volcanoes in Antarctica. So the geology of Antarctica is actually kind of very much bimodal. What's called East Antarctica is basically like the Canadian Shield. There's not been anything interesting geologically for sort of 2 billion years. But West Antarctica sits on a region which is kind of rifting and stretching open. And Mount Erebus sits kind of on the boundary between those two regions. A lot of interest is going on into the actual thermal conditions below the ice, because that is a key parameter in understanding the stability of ice sheets as they melt. So there's been quite a number of groups going down doing magnetotellurics in this area, trying to understand what exactly is the geology below the ice. You've got a kilometer of ice, you simply cannot see the rock type. It's very difficult to see below that. So Mount Erebus was first seen by the Ross expedition in 1841, and has been sort of persistently active ever since. So this is a picture I took on the first time we worked there. So this is frozen sea ice, this is seals for scale, and a glacial tongue. And the summit here is kind of pretty common on a calm day. There's a plume of smoke or steam and other gases coming out. So this kind of does make surface access for geophysics quite challenging, because about 99% of Ross Island is covered with heavily crevassed glaciers. So on a clear day, this is the summit of Mount Erebus. And if you kind of zoom in, you can kind of see various steam vents that sit around the summit. So inside the crater, there is actually this small lava lake. Not many of these around the world. You have to have a very careful balance between magma bringing heat in and the crystallization rate of the rock. So at Erebus, I'll show you in a minute, there seems to be this continuity that the magma is coming up and there is no kind of blockage in the pipe, if you like. A lot of volcanoes have these stages. It comes up and it stops, up and stops. At Erebus, it seems to actually be open. So you get lots of small eruptions. So before you ever work in Antarctica, kind of safety is quite a big issue. So they make you go camping usually on the first night to make sure you know how to sleep in a tent. And if you pass that, then you can you're allowed to go out and make measurements. So this is taken from Scott Base, which is about 25 kilometers from the summit. Very, very hard to judge the scale here, but the summit's 3,400 meters. So we adapt our equipment a little bit to work on ice in a place like Antarctica. So the central part of the instrument sits here. We put in these 3 sensors for the magnetic field measurements. And to measure our electric fields, we lay cables on the ground, put electrodes at the end, and connect all of that up. So obviously with the helicopter access, you can avoid all the kind of inconvenient things like crevasses that maybe complicate life. And to measure the electric fields, we don't put liquids in the ground, that would freeze at -20. So we use these metal plates. So once you have the system going and you have pilots who kind of know what you want to do, it's quite effective. So obviously the pictures are always taken on the days when the weather is good. Here we're burying a magnetic sensor, and here we're setting up the equipment to run. This is the solar panel, it looks like a coffee table, and here we're laying out some cables. So you go through spells in Antarctica, you've been there 3 or 4 days, you have good weather, you get a lot done, and a storm comes in, nothing happens, and then you sit around trying to catch up. So this is one of our higher sites. This is actually quite close to the summit of Mount Erebus. And this was kind of, we were working overnight because that was when there was more helicopter time. So this was kind of, well, a bit like being back in Canada actually. It was -30 when we were up here. And with the altitude, it kind of, you start to get a really bad headache after about an hour. But it's kind of quite a productive way to work around. So the steam vents on Erebus are kind of really interesting. Wherever there's a crack, the steam comes up and it actually forms these large towers of ice, which are really quite unique. And from above, kind of in low light, you can see these are about 2 to 3 meters high. So the main result from Mount Erebus, we collected data at all of these points across Ross Island. And this took 3 field seasons to do this. Working on the glaciers is fine. On the sea ice is kind of problematic. It's really not a very stable surface. But we had a grid that was kind of broad enough. And after processing, what we kind of see is that actually the molten rock is really different to below the Andes. It seems to be this open passageway going from, you know, depths of maybe at least 30 kilometers here in the red up to the surface. So this type of volcano is very, very different to what you have in the Andes. And it's significant because Erebus itself is emitting large amounts of carbon dioxide that have a very high impact in terms of the climate at these very, very high latitudes. So that's kind of a summary of Mount Erebus. I'll just talk a little bit now to sort of conclude about what we do in geothermal exploration. So we use essentially the same equipment. And in some ways, we're studying exactly the same thing. We're wanting to work out where is molten rock, but also where is hot water that we could be using to put into a power plant. So this is one of the techniques that is used widely in geothermal exploration. And a very common scenario is shown in the model on the right. This is from a commercial survey in Indonesia, which, as you saw, is like the #2 world producer for geothermal power. So each of the triangles is a measurement location, and you can see here that this is a producing geothermal field, so they've drilled holes to bring up the hot water. So we typically see this sort of 3 layers. Up at the surface, there's this blue layer. That's typically dry volcanic rock. Then we get a layer of clay. So clay in geology is a type of mineral, and it's often produced by hot water reacting and dissolving rock. So we often see clay at the top of our geothermal fields. So where the clay ends and the blue begins again, that's often the place we want to get into to drill. So clay breaks down, we know, at 200 centigrade. So the bottom of the red layer is often what we're really looking at. And in this case here, you can see that that's about 1 kilometer below surface. So these wells have all gone to 2 kilometers. So the geophysics tells you the geometry of the layers. And it's way cheaper to do this first and then drill in the most prospective locations. So we've kind of worked a lot with this method in Canada and elsewhere. And Magnetotellurics, as we call it, these radio waves, is one of the most effective methods. But geophysics is always better if we combine it with different types of measurement. So in this particular study, they were making seismic measurements. They were measuring small earthquakes that were caused by the extraction of hot water. They measure the pull of gravity to get extra information about the rock density. So this particular study is a very good example of how different types of geophysics together gives you a result which is a lot more valuable than just the individual components that you could have done. So I'll give you now an example from Canada. Canada, as I've mentioned earlier, does not currently produce any electricity from geothermal power. And that is despite the fact that the Canadian geology is very favorable. It's very similar to what they have in places such as the Philippines, Indonesia, and in the Western United States. So here we are kind of in Western Canada, it's the US border, and we have a line of volcanoes, one of these volcanic arcs, just like in the Andes, that extends upwards and sort of dies out once you get past northern Vancouver Island. So this is a belt of 3 or 4 volcanoes. People are always very reluctant to say, well, are they active or are they extinct? I think the consensus is they are certainly not extinct. They show low-level signs of activity. So what we've been trying to do again is the same measurements tell us about geothermal energy, and they're also telling us about the potential for future volcanic eruptions, because we're measuring how much molten rock is down there. So this is actually, I spent most of the pandemic doing this. We couldn't travel overseas to do field work, and we'd sort of got this project started in 2019. So we were able to, through various ways, carry on with these measurements. So this is actually about 3 years' work getting most of these measurement points. So probably about half of them are helicopter access, half of them, if there's a logging road, we'll drive up that. So it's kind of we're very flexible how we get places. So Mount Meager, no surprise, all these red dots are our measurements around Mount Meager. Mount Meager is the most active volcano in Western Canada. And 2,500 years ago, it had a pretty big eruption like Mount St. Helens in 1980. But it's been quiet ever since. Everyone who hikes up there knows about the hot springs that you can kind of find on the banks of this glacial river. And in the 1980s, the Canadian government actually drilled through an energy program and found water at 250 centigrade, very near the surface. But the challenge here was that the distance from the hot water to the power grid was actually quite significant. And that can be enough to tip the economics against development of this type of system. Other uncertainties came up. Temperature is good, but remember, you need the rock to be permeable. There have to be fractures to let the water go through. So there was some concerns about that. But beginning in 2019, 2020, 2022, we actually moved forward and actually collected quite a bit of data at Mount Meager and have a much better idea now of what's below there. During this time, it was actually kind of discovered that Mount Meager had these big steam vents. So you can kind of see these circular shaped holes here. If you kind of, the pilot, the second year I went, had worked out a way to kind of put the nose of the helicopter into the cave. And when everyone started choking, he would move away. But these things are emitting a lot of hydrogen sulfide, H2S. So clear evidence that that's coming from magma somewhere. The debate is the volcano waking up, or is this simply because the ice thickness is reduced and the hot water and steam has burnt through the ice? I'd say people are kind of divided on that question. But either way, it kind of shows we're dealing with something which still has high temperatures in the subsurface. So certainly up on Mount Meager itself, this is the summit of the volcano. It's kind of highly eroded. So sometime in the past, it would have been 1,000 meters higher, a nice conical volcano. Right now, all you can kind of see is the plug. But the heat is kind of definitely down there. So these type of surveys do hinge around. We get an okay or a good weather day. We'll go and put equipment out. We'll set it up. We check it. Typically takes about an hour and a half, 2 hours. That pilot usually will then come back from some other job. They don't always shut down, so we're kind of quite used to, load in, load out sort of very quickly. And then 2-minute flight to the next place and then do it again. There's always a risk you end up camping on these things. If the helicopter has a problem or the weather changes, you need to be prepared to be there for a while. But it doesn't happen too often. In the summer, at least, it's kind of warm. So at the end of the day, we kind of have come up again with one of these models as to what is below the surface. So this is focused in on Mount Meager, and it kind of illustrates some of the different things that are going on. So this is the geothermal area here, where you have a very good grid of stations. This is the place where we had the caves, the steam vents. But another big hazard in volcanoes that is kind of very important is that actually eruptions are not the biggest danger. Landslides on volcanoes are often the big hazard. So 2010, there was this huge landslide at Mount Meager. It kind of came down this valley, it came up this hillside and went upstream. It took out all of the roads. So about this time, companies were debating about starting power production. And this is yet one more factor that they want to consider in terms of risks. So here are the results of our data collection. This is about 3 years' work. And what we start to see is here is Mount Meager itself sitting here. And at about 5 kilometers below sea level, there is this big red blob. So we go through our usual analysis. To explain this rock property, we need to have about 20 or 30% molten rock. So that's not really eruptible, but it's probably is a very, very good heat source that is going to provide continued heat for this type of eruption. So near the surface, if you remember, we see these clay layers. Clay layers are often the things that seal in the hot water. So below Mount Meager, we see a number of these clay layers, and they're all sitting up here at the surface. So we've been really focused in now on denser data collection around these areas, trying to get better locations for drilling. Again, the idea is to reduce the risk of economic costs. Often with these projects, we come down to things which are not scientific. So in Canada, each province has very different energy generation strategies. And British Columbia has a lot of big hydroelectric dams, and they're really quite reluctant to do something different. But I think there are good moves here that they're going to be moving towards more geothermal. So just moving on to the final example, and this is from Iceland, somewhere where everyone's very familiar with geothermal energy. And this example shows two things. First of all, that you can actually be doing both things at once. This is an example that combines the geothermal with the volcano studies. And it also shows a case where perhaps the initial data interpretation was incorrect. So Iceland sits on this boundary between the North American and the European tectonic plates. And we're currently seeing a lot of volcanic eruptions in the Reykjanes Peninsula here. In central Iceland, activity in the past century has been more focused in the north, and particularly up here in Krafla in the northeast. So Krafla went through this episode called the Krafla fires in the 1980s, when there were these big basalt flows erupted. And right in that area is one of the Icelandic power stations. So this kind of runs, I think it's a several hundred megawatt power plant. So the idea has been to look in Iceland at finding new ways of getting geothermal power production. So a typical geothermal well with 200 centigrade, you can probably get, 10 megawatts electric. The idea has been if you drill deeper, you can get into high temperatures. Don't want to go too deep that you get into molten rock, but deeper where you're getting maybe 400 centigrade, you could increase the power production 10 times from a particular well. So a number of Icelandic projects have tried this deeper drilling to see what is going on at greater depths. And Krafla was one of the locations where they did this. They drilled this IDDP1 well. And before they drilled that, Icelanders, they use electromagnetic methods. So their analysis showed that there were these two red regions, which they thought were magma. So they decided to drill in between them so that the drilling wouldn't intersect magma. Because if you drill into molten rock, it doesn't really end well. Well, unfortunately, something happened. And 2 kilometers down, this well, suddenly the drill bit started moving forward quickly because they were into molten rock. So I think immediately the first thing that happened was they pointed at the geophysicists and said, well, you told us there was no magma here. So the consensus is probably that they just hit a small layer of molten rock. Now, this has happened elsewhere in Iceland. It's happened in Kenya. So it kind of illustrates that you have to kind of be careful drilling in these regions. So the well did not erupt. What's happening on the left is they cleaned out the well. They pumped steam down, and it's bringing up a lot of rock fragments. But they did not continue drilling here. So obviously, if you can get down closer to this heat source, there's good evidence that you could be getting fluids at 400 centigrade, which would be an order of magnitude more power. So obviously, this may have a future, but we have to address this issue of how do you detect magma ahead of the actual drilling. So I spent a while with my students after this happened trying to work out, well, why did they miss the magma? And I think the simple conclusion is that it was too small a layer to be detectable from the surface. So the initial analysis had used kind of quite a simple layered model approach. We tried a 3D approach. And regardless of how you do this, you are struggling to get there and see into these molten rock layers. So Iceland certainly has a great future with this type of power. And obviously, if they can find a way of moving that power by a submarine cable to other countries, then there will be someone to buy all of that electricity. But this is kind of one of the frontier areas. The Japanese are working in this area too. And a lot of it hinges on using geophysics to actually sort of know what you're drilling into. So just to kind of conclude, that's just kind of a very short overview of a number of different projects showing with geophysics how we're looking to find out what is below the surface. And the things we're looking for, particularly in these volcano geothermal studies, is first of all, where is the rock molten? How much is there? Could there be an eruption? But also, how much salt water is down there? How much of these brines can we locate? And then try and work out, okay, if we're going to develop geothermal energy, where do we do this? So as John mentioned, we're involved in a project on Montserrat, which is a volcanic island in the Caribbean. It's now almost 30 years since the eruption there began in 1995. And the idea is to try and find places where we can extract the hot water for heating, for power generation, and also those waters are full of dissolved metals that could be used. You know, current practice is to put them back where they came from. So being able to combine different economic activities would be incredibly valuable. So this type of imaging, MT, has really advanced in the last decade, and talked a little bit in this talk about how that happened. And I think one of the conclusions I come up with, every volcano we go to, it's kind of like talking about the weather. I think every day is different. The weather is, each of these volcanoes has its own structure, but we're starting to get enough of them now that we can see sort of certain patterns, at what depth you would expect to see certain things. So I'd be very happy to take any questions, and thank you again for your attention. Great.
Sit down here. And,
yeah, thank you.
Okay, well, thank you very much, Martin, for a really informative and well illustrated talk. I invite questions from the floor. I would remind you, we are being recorded, so temper your questions accordingly. And you would need a microphone so that those online can hear. So if I could take the gentleman at the back there first, please.
I'm just curious, in oil exploration, they use different techniques. They set off explosions.
Yes.
And then look at the changes. And why don't you use these techniques?
Right, so in seismic exploration, you're sending a sound wave through the ground. We're sending a radio wave through the ground. When you're looking for, say, a contrast between dry rock and wet rock, you get a very large change in the material property between those two. So that's not to say actually quite a lot of geophysical data in geothermal seismic is also used. For example, if you're looking at layers and faults, you can use that as well. But it's the fact that the change in property that we measure is 100. The seismic velocity might change by 20, 30%. So that's the basic reason. Yeah.
Hi, thank you. So you talked a lot about field methods and
Yes.
physical methods for detecting geothermal reservoirs and
Yes.
such. So could you maybe talk a bit more about empirical or maybe like remote sensing types of ways for detecting that stuff? Because it seems there's maybe potential for using Landsat, for example, to detect surface level anomalies. So I guess in your opinion, does that augment, replace, or is it insufficient to kind of do what field work is doing right now?
So with remote sensing from satellites, you can see changes in mineral content, you can see changes in temperature, changes in plant types. That is all used in the early stages of geothermal exploration. But there often comes a point they don't give you information below the surface, any significant distance. So, geophysics, if you can do it from an airborne platform, it becomes much, much more efficient. But you can't really move up with this type of method, say, to satellite elevations, because you're just so far from the target that you would not be able to resolve structures a few hundred meters across. But certainly sort of Landsat type remote sensing is used in the early stages. Sometimes, depending on the location, people go measuring, very subtle changes in certain, in the chemistry of tree branches, because if you've got fluids coming up, you'll see changes in certain elements. So it's part of the process that is used, but you need to use, to go deeper, you really have to use geophysical methods. And some of them can work completely from the air. If you want to look 500 meters down, you can do a lot of that from an airborne system. But really, if you're going below 500 meters, you have to kind of land and put sensors in and stay for a while to get the data. Yeah. Sure.
Oh. Charles.
That was a great talk. Could you say a little bit about earthquakes and geothermal?
Yes.
Because I believe there's been pushback in places like Central Europe from that.
Yeah.
And can it be controlled at all by just how you do the brine extraction and injection?
Okay. So that is one of the, I didn't give a full list of the negative things of geothermal, but there's been a number of documented cases where they have generated small earthquakes. And very similar things occur in, for example, oil and gas extraction. So often when you're either pumping water in to fracture the rock or you're just disposing of wastewater, it's essentially the same process. So I think one of the most high-profile cases was in Basel in Switzerland, where they were developing a geothermal plant, primarily to heat petrochemical works in Switzerland. And that triggered a set of, they wouldn't be considered large in Vancouver, but they were, if you're in the middle of Europe, away from fault zones. So that project essentially got shut down. It was just perceived that, you know, even a magnitude 3 or 4 earthquake with buildings that were not built with that in mind was not really acceptable. They're not geothermally caused, but in Alberta we have routinely small earthquakes caused by oil and gas extraction. So there they have a system that they measure the size of the earthquakes, and if they exceed a certain threshold, which I think is like magnitude 3, you know, the operator has to pause and find out what's going on. If they exceed, I think it's 4.5, they are shut down for a while. So each of those studies is kind of case persist, you know, but places like Iceland, people are living right by the fault zone. You know, you have to adapt to what are the societal expectations, but it is one of those consequences, you know, which does have to be taken into account. Obviously, if you're in a remote area, it's not going to be an issue. But if you're where people have been living already and you're the newcomer, then that has to be recognized, I think. Yeah.
Okay, and then we'll go back to this. That's fine.
Thank you so much for that really fascinating talk. It's really, what do you feel the potential is for geothermal energy globally and its contribution to our energy mix?
So one of the things that's happened since I've been working with geothermal is, you know, other renewables have become a lot more economic, you know, particularly photovoltaic for solar power. You know, the cost of those panels has come down. And wind power, you know, I think the UK does a lot better than Canada does in that regard. But each of these non-renewables, I think, really works together. There's places where geothermal can make a big, big contribution. And there's places, I think, where I wouldn't quite say don't bother, but I think the money would be better invested elsewhere. So places in Canada, you know, people have come up with estimates for British Columbia having, you know, somewhere possibly up to, say, 5 gigawatts of electric power production. You know, for reference, that's a little bit more than one of the large hydro dams. We have hydro dams in BC, which are 2.5, 3 gigawatts. So you could be, that's the scale you could be looking at. But it's often, we also see, it's sometimes not, if we're in, you know, southern Canada, we're competing with quite cheap electricity. I've worked quite a bit in the north, in the Arctic, in Nunavut, where you're looking at fuel prices and energy prices that are 10 times higher. So that's a place where, you know, geothermal maybe has a niche. But I think the key thing with renewable energy is they all kind of work together. So like we were looking at a geothermal project in the Arctic, and the idea there was they do have like 3 or 4 months of almost continuous sunlight. So you can heat water up. You can't keep it on the surface for winter, but the idea is to put it down a borehole and you heat up the aquifer. So you use the ground as a large battery. So I think geothermal has a huge potential. It's great that there's alternatives, you know, wind power and solar, I think are really kind of, you know, are able to actually now become quite a dependable source of power. But it's one of those elements. As I mentioned in my talk, you know, one of the problems we see in Canada is every province has a very different energy economics. And, you know, British Columbia has abundant hydroelectricity, you know, but it also has the best geothermal resources. So, you know, it's really trying to have a sort of a larger scale national approach to energy policy. That's, I think, one of the key things.
I find this example in Iceland where the drilling hit a molten layer interesting because it also shows the limits of our geophysical methods. And I wanted to know whether you have any way to assess the limits of this MT method when you say, oh, we can drill here, it's safe, and maybe say, unless there is this structure that we couldn't spot.
So you're asking about the uncertainty in the analysis?
The uncertainties and maybe the resolution as well of these images.
So anything with geophysics, as soon as you start doing this, you know, it's kind of, well, in Calgary, where Mike's from, you know, a lot of our students used to go to Calgary and work in the oil industry, and geophysics would be referred to in some uncomplimentary ways because there are uncertainties. You know, people were very comfortable if they drilled an oil well and you can actually look at the rock sample and you know what it is. You can say 3,000 meters down, we've got shale. As soon as you're using geophysics, there is some uncertainty. So for every one of these colored images that I show you, we've gone through a process of just trying different processing parameters. We've tried various tests, you know, take this feature out, make it stronger, make it weaker. And so any model we show has been through this test. A rule of thumb probably is that where you see those low resistivity, those red horizons, you can get the depth to within probably 10%. Seeing deeper, you get into problems where the layer can attenuate the signals. But we do go through these models and undertake this sort of analysis. Okay, what would we be able to say? You know, what can we have confidence in and what is not resolved? And again, often just combining with different geophysical methods. You know, if you're looking at oil and gas reservoir structures, seismic reflection is the way to go. It can see things, 20, 30 meters thick. But if you have problems getting the signal down there, the MT, the electromagnetic, can give you an alternative image. So this has been a real trend. We process different types of data together and, bringing in all available information. But absolutely, geophysics is non-unique.
Lawrence.
Thank you. I visited a site once in Japan where they were extracting the scale from geothermal pipes and taking the gold and the silver that was in the scale in the pipes out, processing it, and making that contribute to the overall cost of the extraction. And that's often the case, that these geothermal systems are also epithermal in terms of their ability to I guess, concentrate precious metals in the surface environment. Would that, if it was not more widely applied, would that not contribute to the overall cost structure of making these geothermal sites more viable?
Well, that's certainly a big part of the project on Montserrat, is to do that. But you're right, it's kind of surprising looking back that this has not become a sort of mainstream activity. I've seen some of the figures. I mean, some of these plants, they're putting tons of silver back into the ground every year. So, I think the countries that rely on geothermal electricity, their economic model works. It's sufficiently cheap and predictable that they don't really want to then sort of, have an extra sort of piece of plumbing that goes between the injector well and the reservoir. But absolutely, like in Alberta, it's a sedimentary basin. It's the same. You can get lithium out of those waters. Not everywhere, but in some locations, the concentrations are sufficiently high that you can be doing. It can be economic, but it's. No, the whole kind of, there comes a point with a lot of these things where it goes beyond the technical aspects. It's how the companies are making money, and quite often it gets into political things. Certainly in Canada, that's the case, that each province has its own mold for how they generate electricity, and they want to keep it simple, I think, is one way of looking at it.
Mike, I think that's...
Thanks, Martin. That was a great talk. You didn't talk much about engineered geothermal systems. And I guess my question is, can you use Magnetotellurics to, so there you're trying to find hot areas, not necessarily wet areas. And how well would MT work in detecting temperature as opposed to fluids?
So in engineering geothermal systems, that's where you actually create the porosity. If you have the heat but not the fractured rock, you use hydrofracturing to fracture the rock. So we, at one point, the Alberta government was kind of, well, Shell actually before them had been actually looking quite seriously at several places to use this as a power generation method. And it requires a different type of exploration. You're looking at the temperatures. To a first order, electromagnetic geophysics is not very sensitive to temperature. There is an effect, but it gets overwhelmed by the fact changes in water chemistry will have a big effect. Once you start producing, there's been some cases in Australia where they've been fracturing the rock for EGS, and they've been able to use surface MT geophysics to see how far the fracturing has gone. That doesn't really work very well from the surface because you're so far away from the target, but you always have boreholes in those cases. So borehole geophysics, be the sort of microseismicity that Mike works with, or you can do electromagnetics from boreholes as well. That gets you close up to the target. And again, you've already invested the money and drilled the holes, but at least you know what's kind of around your borehole and maybe where you're going to place the next one. So to first order, I would say no, we don't have a temperature dependence. It's primarily the rock type and the amount of water in the fractures and whether it's connected that we're really sort of able to focus on.
Okay, I think we'll stop there. I hope Martyn's conveyed a sense of the great potential of geothermal, a potential that's to a large extent unrealized because the focus has been primarily on generating electricity. And there is a whole value chain of benefits that currently aren't accessed and would dramatically change the economics. And in answer to an earlier question, a fun fact, if you like, is that Rotokawa power plant in New Zealand produces 57 tons a year of silver dissolved in the fluids that go into the turbines. And 57 tons of silver is re-injected back into the ground on the other side of the field. Because mercury power, they don't do metals, and that's that. So there's a very interesting intersection of science and economics, and a lot of the issues that Martyn referred to is about willpower.
Yeah.
And that's beyond what the scientists can do, but that's part of this reset program that the Martyn School has funded. Anyway, thank you very much, Martyn, for a fabulous talk, and thank you for your attention.
Great, thanks.